Okay, let's get started with 2-1 intercept symmetry and graphing key equations. So, a couple objectives here today. We're going to first find intercepts algebraically from an equation. So, up till now we've been looking at a graph and we've been saying, okay, the x-intercepts here are -4 and -1 and 4. Those would be your x-intercepts. And then your y-intercept would be down here, right? We're just looking at it visually off of the graph. The y-intercept would be -3. All right, what we're going to want to do now is be able to find the intercepts without using the graph, just from the equation. And here we go. To find the x-intercepts, we're going to let y be 0. Because if you're on the x-axis, y is 0. And then to find the y-intercepts, that means you're on the y-axis, x is 0, the opposite. All right, so let's try this here. We have the equation of y equals x squared minus 9. First, let's find the y-intercept, because that's actually the easiest thing to do. Because the y-intercept, we just make x 0. So y equals 0 squared minus 9. 0 squared minus 9 is -9. All right, we got ourselves a y-intercept. Let's go ahead and find the x-intercepts. And on here, I know there's going to be 2 because this is an x squared problem. So x-intercepts, we're going to make y 0. Y is 0. So x squared minus 9. Let's solve for x. Let's go ahead and factor here. 0 is x minus 3 and x plus 3. And so x is plus or minus 3. So there's our x-intercepts. So let's go ahead and graph this. Just sketch of this. 1, 2, 3. 1, 2, 3. We're going to go down 9. 1, 2, 3, 4. Need a little more room. 5, 6, 7, 8, 9. And this is a symmetric parabola. Oh, this is going to be an ugly drawing. I apologize. You're going to sketch that much prettier than I just did right there. But you get the idea. We've got our x-intercepts and we've got our y-intercept there. All right, go ahead and try problem 13. Okay, second objective. Let's test an equation for symmetry. So, looking at this graph right here, we have 2 different curves here. We have this one, boing, and we have this one here. And this is symmetric about the x-axis, all right? So we say symmetric with respect to the x-axis if every single point has the exact same x value and the y values are opposites. So negative y matches up with y. Same x, negative y matches up with positive y. Okay? You can think about it as if we folded over the x-axis, every single point would land right on top of its partner on the other side. Okay? We can also do the y-axis symmetry, symmetric with respect to the y-axis. Every single point is going to have the same y value, but opposite x values. And then lastly, we can be symmetric with respect to the origin, where the x and the y's are both flipped, right? So we're actually going to spin 180 degrees and land diagonally about the line y equals x. Okay, so we draw a diagonal folding line, y equals x, and we would fold over that and land on the same spot. Okay, so here's your example. I would maybe put this in your notes here. There's the 3 different visuals of your different symmetries. X-axis symmetry, we have symmetry with the origin, and we have, oh, there's a repeat there. I don't know why they put this twice. We should have another drawing here. Symmetry with respect to the y-axis. So let me sketch one in. If we're doing this, and we fold it over, we could have it like that. So y equals x squared is symmetric to the y-axis. Okay, so let's try a problem. If a graph is symmetric with respect to the x-axis, and the point -2, 3 is on the graph, then what point is also on the graph? So -2, 3, it's over here, -2, 3. And so if we're symmetric to the x-axis, that means we need another point down here. X value stays the same, -2, but the y value changes, -3. What if we had -1, 3? that in there. If we have -1, 3, so maybe up here, and we're symmetric to the y-axis, then we're going to fold over the y-axis, and up over here, the y value stays the same, but the x value switches. And lastly, -1, 3, if we're symmetric with the origin, if we started here, we need to change the -1 to a +1, but also the 3 to a -3. So we're down here. So -1, -3, sorry, +1, the opposite of -1. 1, -3 would be the point that would be on it if we were symmetric with respect to the origin. All right, take all that in and see if you can try problem 21. So now we have some tests algebraically to see if we can figure out if we have x or y or origin symmetries. And so firstly, we're going to, for the equation, find the intercepts. We can review doing that quickly. I'm going to find the y one first. Y equals, plug in 0. 0 minus 9 is -9. 0 plus 2 is 2. So my y-intercept is 0, -9/2. Let's go ahead and solve for the x-intercepts here. 0 equals x squared minus 9 all over x squared plus 2. Now the nice thing here is that if I multiply both sides by x squared plus 2, 0 times x squared plus 2, still 0. These will cancel, so we have 0 equals x squared minus 9. And we know that this is going to be a -3 and a +3. So we have our x-intercepts as, plus or minus 3, 0. We'd have 2 of them. All right, let's go ahead and test for symmetry real quick here. Clear the screen. And so now, if we want to find the intercepts here, so let's go back to our test. The x-axis symmetry, replace y with -y and see if you get an equivalent equation to result. All right, so I'm going to go over here. We had y before. If I say -y equals x squared minus 9 over x squared plus 2, is that the same thing? No, it's the negative version. This negative didn't go away, so we have no x-axis symmetry. If we look here for y-axis, we replace x with -x. So let's take a look at this. So y stays the same. X becomes -x squared minus 9 all over -x. We're replacing x with -x plus 2. Now what happens if you square -x? You get back to +x squared minus 9 and +x squared plus 2. That's the exact same thing as what we started with. So we do have y-axis symmetry. And so on this one, we would not have origin symmetry, because origin symmetry would have to say -y equals -x squared minus 9 over -x squared plus 2. And so that's going to say -y, does that equal x squared minus 9 over x squared plus 2? Is that what we started with? No, it is not. Okay, so no origin symmetry. And there you go. We've got our 3 tests. So after doing that, let's try problem 51. All right, last thing here. 3 key equations that you need to know. You're not going to try any of these problems. You just need to have these down in your notes as equations we use a lot. Y equals x cubed. You should be able to plot this by hand, no problem. Here's the important points for x cubed. X is 0, 1, 2, 3. That makes y 0 cubed is 0. 3 cubed is 27. That makes y 0, 1, 8, and 27. If you go ahead and plot this for -3 all the way to +3, you'll get these values, right? -3 cubed is -27, and the graph will look like this. Okay, so you need to know the general shape of y cubed, and you need to know the values that go with y cubed. Have those in your notes. We're going to use them in the future. You also need to know y squared. Okay, so we look at this. We plug in numbers for y. We get these results for x. And we get a graph that looks like this. We haven't dealt much with this before. Y squared, okay, we turn the graph sideways. For those of you that have talked about functions before, this is not a function, okay, but we're going to graph it just like that. So have that one down. Pause the video if you need to. Get those values down. Lastly, oh, sorry, there you go. That's what we're getting on our calculator. Lastly, 1 over x is a function that we need to know about. Okay, so there's some good values that you can start with. You might want to pause the video, get those down. But the graph looks like this. Okay, we're going to have quadrant 1 and quadrant 3 curves for 1 over x. All right, we'll work with these equations in the future. For the time being, if you've got any questions, we'll go over them in class. Good luck with those problems that are for you to try. All right, see you in class.